Hello, welcome to 7.4, Restrictions on Radical Expressions and Functions. So in this lesson, we are going to be looking at our radical functions as well as some rational exponent functions and just kind of talking about the domain, some restrictions that we might see, but here's a quick little warm-up. Remember that when we are solving for x in these cases, we want to isolate the power, take the appropriate root of both sides if it requires a root. In this first example, you're going to see it doesn't need that. And then just complete with the opposite operations. So in this case, here, to get rid of x to the 1/3, we always want our answer to be x to the first. So to do that, we could think of this as a cubed root of x, if I just rewrite it. And to undo a cube, we would take it to the third power. Or if you don't like that option, if you want to save yourself a step without the rewrite, you can just cube both sides here. Because what ends up happening is the 1/3 times 3 becomes 1. So then we do get the answer of x equals 6 to the third. And you can multiply this out. It does give you 216 for your answer. Here's our next one. We have negative 3x to the fourth equals negative 81. In this case, I would suggest divide by negative 3. This one is not going to work out super nicely. It would be x to the fourth equals 27. And then when we take the fourth root here, because I want to do the opposite, I would get x equals plus or minus. This won't break into a perfect fourth root because 27 is a perfect cube, so it's just short. So we're going to leave our answers plus or minus the fourth root of 27. Now note, I did plus or minus because this is a fourth root. If it's an even root, you have to remember to do the plus or minus part. Last one here, this is the one where you want to isolate the parentheses, get the x plus 4 by itself. So we do the reverse order of operations. So I would add 3 to give us 12. We'd have 2 times x plus 4 squared. Then we would divide by 2. Now we have the parentheses isolated, which has our variable. Then we take the square root of both sides. And in this case, it's x plus 4 equals, don't forget the plus or minus, because it was an even root we took. And then we would subtract 4 from both sides. And this is actually a problem that we did back in unit 3. So this would be x equals plus or minus, let me put the 4 first. Negative 4, then the plus or minus the square root of 6. Okay, now we want to list the restrictions on x for each expression or equation so that it can be evaluated in the real number system. And if there are no restrictions, state that there are no restrictions. So we're just looking for the values where we would get imaginary solutions basically because we want to stick to the real numbers. So we can take the square root of anything that isn't a negative. Like in our first example here, the square root of x. So the restrictions that we could have here is any negative number. And negative numbers start before 0. So how we're going to write our domain in this case is we are going to say that x has to be greater than or equal to 0. Now you can write this in the set notation as well. So set notation for this would be includes 0 and then everything be above 0, 0 or greater. This next one is a cubed root. Cubed roots, remember, it's okay to have a negative value, so there's actually no restrictions here. We're never going to be able to get an imaginary solution from a cubed root, in this instance at least. So in that case, there's no restrictions on our problems here. Okay. And then this one, even though there's no square root or anything like that, we saw this in the last unit, unit 6, when we were talking about those rational expressions. You can't have a 0 in your denominator for a rational expression. So the value that would make this 0 is x cannot equal positive 3. Like if we were to set this equal to 0, that's the value that would make the denominator 0. And then we would also need to write that x is an element of the real numbers. Or if you want to do this with set notation, you can go like this. So it would be from negative infinity to 3. You don't do the closed bracket. Then it would be union 3 to positive infinity. This just shows that you cannot equal 3. Okay, now we're going to go to our next set here, list the restrictions on x for each expression. And then, again, we're trying to get answers that are in the real number system, so no imaginaries and no restricted answers, like what we saw with that fraction up above. So the first one, g of x equals 3x minus 4, this is a linear equation. There's no value that we can't plug in for x. Nothing is going to make this impossible. We can't get an imaginary solution out of this. So this is a good example of a no restriction or restrictions. The second one, since this is a square root, we will have some restrictions here. We want to think about, well, what are the values inside of the square root that are going to restrict us? This time it's a little different though. Like here, it was just the square root of x, so we knew everything had to be positive. So in this case, we need to think about, well, underneath the square root, where are the negative numbers going to start happening? And in this case, if we're subtracting 4, let's set that equal to 0, so we think about where our negative numbers are. If I add 4 to both sides, I would get x equals 4. So it's all the numbers that are smaller than 4, because if I were to plug in like a 3 in place of that x here, 3 minus 4 would give us -1. That'd be an imaginary, and we don't want any imaginary solutions here. So then for this problem, we are going to say x has to be greater than or equal to 4, because it can be 0 under the square root. And again, if you want to write that in the set notation, it would be 4 to infinity. This one here, we got a cubed root. There's nothing else here, no fractions with any variables in the denominator, no square roots, no even roots. So this is just going to be a no restriction. Okay, now we have a few more that we want to actually solve here and think about any domain restrictions. So in this case, I'm going to do that right away. I'm going to think about how do I want to write this. Since I'm taking the square root of x minus 2, again, it's kind of like that situation we saw up here where we were subtracting a number from x. So we know that the values actually are going to start at positive 2, because if I plug in 2 for x, then I would get 0. So I need all of my answers, or however many answers I get, they got to be bigger than 2 or at 2, which is the same as 2 to infinity. Now, we haven't solved one like this just yet, but the way that we're going to do it is the inverse operation of a square root, which is to square both sides. And we're going to just square that entire square root. So these are inverse operations. So we're just left with what's inside, the x minus 2. And then here, 6 squared is 36. So we would add 2 to both sides. We would get x equals 38. And 38 is a good answer. It's greater than or equal to 2, so it doesn't violate our restrictions. The next one here says solve and state domain restrictions, if any. So we're going to do the exact same thing. We're going to think about, well, what is the value we can't have under the square root? And that would start at 0, since that's the only term under is an x. So x is greater than or equal to 0, or we would write that as 0 to infinity, like this. And we're going to do the same thing. We're going to square both sides, because we have a square root for this variable here. So this side becomes just plain old x. This side, however, I squared both parts because I have to include the entire expression. So this becomes x minus 2 times x minus 2. So we're going to have to do the FOIL process. So x equals x squared minus 2x minus another 2x and then plus 4. I'm going to combine my like terms on the other side to give us negative 4x plus 4. And then I'm going to subtract x, and this one does seem like it should work out nicely. So we'll get 0 equals x squared minus 5x plus 4, and this will factor into two nice answers here of x minus 4 and x minus 1. Factors of 4 that add to make 5. So then our solutions would be the opposite. It would be x equals 4 and x equals 1. I'm going to quickly double check those two answers with my restrictions. They're both bigger than 0, so they work. These are viable solutions. Last problem here says solve and state domain restrictions if we have any. So for this one, x minus 2, and then it's to the 3/2 power. In this case, I want to write it in the radical form because when we see that radical notation, it's easier for us to think about restrictions. So remember, the denominator is your index, so this would be a square root of x minus 2. Then we could put this to the third power like this. So the square root of x minus 2, we do have restrictions on square roots. So that tells us that we need to make sure to have our values be greater than or equal to, in this case, if I were to solve for x minus 2, I would get positive 2. So I want all my values to be bigger than 2 or at 2. So from 2 to infinity for our set notation. Now to undo this one, to undo a cube, we actually have to take the cubed root of both sides. And this problem is going to work out really nicely because 64 is a perfect cube. Here, our cube and our cubed root would leave us with the square root of x minus 2. And then the cubed root of 64, that's 8, actually, let me do it this way. 4 and 16, and then 16 breaks into 4 and 4. It's a perfect cube, so I just wanted to shortcut that. Then we would square both sides like we did up above. We would get x minus 2 equals 16, because 4 squared is 16. Then I'm going to add 2 to both sides. We get x equals 18 as our answer. And that is a viable answer because it is greater than or equal to 2. Eventually, we are going to run into some examples where we have restricted answers, and we'll talk about what to do in those situations.